I'm gonna switch to English because if I don't have any beers in me, my Croatian sucks. And especially technical parts don't really go that well. Before we start, 3 weeks ago we had Community Day Adria, the first of its kind in Podgorica, Montenegro. I didn't see anybody there from this group, but don't worry, we are going to have it next year as well. So this is a regional event we started this year. Next year it's going to be in Sarajevo. The year after that we'll see, maybe in Slovenia, maybe in Zagreb, maybe in Belgrade, but ex-Yugoslavian countries are going to get this event yearly now. So please follow the user groups, whichever you follow, and join us next year, if you will. So I had a talk. Let's see if this thing is going to work. Yeah. The community day about running high-performance workloads on AWS. And this goes back to my time at Bitstamp. So maybe I skipped this part. I used to be head of infrastructure at Bitstamp, this cryptocurrency exchange. Which had a lot of customers. We had to do a lot of high performance computing, really low latency stuff, something that does not come out of the box at the time. Right now you have a lot of more features supported. So we're going to be talking about EC2 stuff, networking stuff, and a little bit of a deep dive into how you can potentially fix your performance issues or not, right? After I left Bitstamp, I was VP of DevOps at this crypto custodian called Qredo. And right now I'm a bit of a freelancer / consultant, so if you have any projects, let me know. We can do stuff together. And how did we end up here? So like I said, this goes back to 2018. Bitstamp at the time had their own in-house matching engine that could process tens of transactions per second. And crypto, this was at the tail end of the bull run in 2018. We were down a lot because of that. So we had a lot of performance issues, right? And our CTO at the time, David, went ahead to this company called Cinnober, which later joined with NASDAQ, and said, yeah, we're gonna buy this black box, this very big new matching engine, and it's gonna be 1,250 times faster, and we're gonna have 400 times as many transactions per second. Which was amazing from a marketing point of view, but if you're an engineer, these numbers are hard to match, right? Anytime you want to do that, it becomes very much problematic. And the blog is live. If you want to go to that link and see what we actually did, you can read the articles, right? But these numbers were very, very scary for me because at the time I was kind of coordinating the project on a technical level with our developers. And with NASDAQ, Cinnober, sorry, so we were trying to put this into the cloud. And before we actually go into the details why this was hard, what exactly is a matching engine? So if you do any kind of trading, you always have buyers and sellers, like you do when you sell used stuff. You set a price, and if somebody agrees to that price, it buys your stuff, right? And matching engine is basically that. It's a very complex piece of software that does matching between buyers and sellers, usually in memory at a very, very, very high throughput rate, right? And why is this so hard to do, to put this into the cloud, right? So the story goes, Cinnober developed the matching engine for on-premise exchanges, such as London Stock Exchange, for NASDAQ, stuff like that. So this is a very complicated piece of software that runs on traditional exchanges, right? And traditional exchanges have operating hours. So if you ever traded on NASDAQ, for example, it opens up at 9 Pacific time and then closes at 5 p.m., right, Pacific time. And when the exchange closes, behind the scene, what sysadmins do basically, you shut down the entire server, the main server, then you recycle it, do some sysadmin stuff, purge disks, rotate logs, everything you need to do to make the system clean for your next morning, Monday, Tuesday, whatever, right? So you have predictable operating hours. You have predictable infrastructure, right? Most of these components run on on-premise data centers. very, very much optimized, latency optimized. You know all the traffic pathways that are happening and how they are happening inside your data center because you obviously built it. And some predictable customer patterns. So what does this mean? You actually very rarely directly talk to a traditional exchange. You always go through a broker. Brokers have rate limits, right? This is not how a crypto exchange that is online works. Every customer can directly connect to an API and do trades. And this traffic patterns become very much unpredictable. So on a high level, like what we needed to accomplish, we bought this black box, right? It was called Trade Express. It had a couple of services running inside. And these services obviously needed to talk to each other. Like an example of a service is a matching engine is one service, order entry is one service, so this is a component that accepts your order. Then you have reporting, so you can fetch data outside, tax service, eMAPI service, a whole bunch of trading components that belong into a matching engine. And this obviously you can't fit it on one instance. Like there's too many components. That's problem number one. Problem number two is you need to have a high availability cluster. So if your primary component goes down, you need to have a secondary component that shares the same state. Right? So think about databases, replicas, stuff like that. Everything has to be in sync so that you can have seamless failovers, right? And then we had an additional problem that we needed to solve, right? So this was a matching engine designed in 2018, designed for on-premise exchanges, right? So remember I said you shut it down, you clean up some stuff and bring it back online, right? So for all of these, let's say for one cluster, if the entire cluster falls down, for example, when you bring it back up, it needs to have the same state. So in order for the cluster to do that, it needs to write a lot of logs, a lot of data to disk. Right? And disk space is not unlimited. Right? So if you have like a few terabytes of data with max IOPS, it becomes really, really expensive on AWS. So we were limited with the disk space that we had. So we had to actually rotate the entire cluster from time to time. This process is not happening anymore, but when we implemented it did, which basically means that we need to do a memory dump between two clusters. NASDAQ wrote the mechanism, we had to support it on the infra level. So memory dump needs to happen as fast as possible, like ideally under a second, but you need to transfer a whole bunch of gigabytes of data between all the components to keep them in sync. Once you do that, you shut down the original cluster, clean it up, wait for another switchover to happen, right? So it becomes fairly obvious that we're dealing with a lot of communication back and forth, certain limitations that we need to overcome, but the performance limitations were always between the communications that were happening between the components, right? Because if you had a lot of latency here, like the secondary components couldn't be in sync, and if they weren't in sync, that means that the original order could not be confirmed until it is in sync, so it obviously slows down, right? So it boils down to networking, right? And the primary question for us was like, where do we place these components? That's like the question mark here. So this is a very, very abstract, high-level presentation, but with every service or a company that you run in AWS, usually have like a front-end service, some back-end services, and for us, we had trading auxiliary services. Think of this as if you open up a trading view, like there's a lot of charts, a lot of blinking stuff that blinks, like WebSockets, and the matching engine that we're putting in. So how do we tie this together to make it work as fast as possible? Right? One of the easiest things that you can do is look at how AWS networking actually works. Right? And we did a very, very deep dive with our AWS TAMs, with service engineers to see how we can get the best latency. Right? So we run in European data centers, or at least while I was part of it, it ran in European data centers, and we had some issues there. But on a high level, like how does the networking infrastructure look like for AWS? So there are a few cells, and you're going to hear like different terminology about this, but there are a few components that are running inside AWS availability zones, right? So the basic component is your rack. And if you've ever been in a data center, you saw like physical racks, you know, the 48 units rack. That's basically it. On top of that, you usually have some patch panels, if you do, or maybe not. But usually on top of every rack is a top of rack switch. So if you are a networking geek, this is where you're going to connect all of your components into, right? And AWS calls this spine cells. If you want to talk between racks, your communication patterns are going to be rack, spine cell, maybe another spine cell, and down the rack. That's how it's happening inside your AZ. Right? If you want to talk between AZs, your traffic patterns need to go through core cells, and think about core cells like your routers. Software-defined networking, but as a basic block, it is your router. Like it routes traffic between availability zones, between physical data centers, right? But inside an AZ, these are your basic components, right? So when you launch an instance, an EC2 instance, by default, it gets randomly placed anywhere in the rack. So you launch an EC2 instance, you launch like 5 in this case, they're going to be randomly placed somewhere, right? And you may get lucky. We figured this out. You actually may get very lucky and you achieve this. So let's say you have 2 instances that need to talk to each other, and you get this random placement that goes through the same top of rack switch. Your latency is going to be pretty good. You may get lucky, or you may not get lucky, right? And then you're going to have traffic patterns such as this. Like these are nanoseconds, milliseconds, like very small units of time, but they do add up if you have a lot of back and forth communication like we had. Right? So one of the first and easiest solutions that you can look at are placement groups. Right? So how many of you guys have used placement groups? 1, 2, 3, all right, a few people. Perfect. Usually you use this type of placement groups. It's called a CPG, a cluster placement group. And basically what it does, it groups your instances in one AZ inside one or more racks that attach to the same spine cell, so the same on-top switch, right? So these are you're going to use them if you want to optimize for high-performance workloads, right? So ideally, when you have a lot of back and forth, low latency, small packets kind of stuff happening, right? This is where you're going to use them. Everything is as close as possible, right? But you're limited to a single top of rack switch, single spine cell. So what that means, here are your instances that you place inside a CPG. If something happens here, like a power supply fails, your switch fails, your workloads are going to be down. That's the but part. Right? So think about if you want to use this or not. But for us, like it was a no-brainer. We had to go with CPGs because this gave us the best performance inside the cluster. Right? The other one is the 2 out of 3. So the second one is the partition placement group. So partition placement group basically means that you can spread your instances across racks inside partition. So each partition equals one rack across an AZ. You're still tied to one AZ, like you don't hop through a core cell, through the software-defined router, but you have better redundancy in case something fails on a physical level, right? Because we all like pictures, this is basically it, like partition 1, partition 2, partition 3, and then you define where you're going to place your instances, right? But partition is basically tied to a rack or to a unit that combines with a spine cell. Personally, I've never used this deployment, and I also never used the last one as well. But you may find workloads that are suitable for this. Right? There are a few limitations. You can only have, as far as I know, and maybe you guys can correct me, you can only have 7 partitions per AZ. Like it doesn't scale above 7. Right? And the last one is spread placement group. So spread placement groups allow you to distribute, again, your instances across racks and across AZs. Right? The only thing that you can have here is that it is going to deploy up to 1 instance per rack. Right? So this is where if you have a redundant application, like microservices, you can run a whole bunch of them. You're going to use this to spread them across racks at least one rack with different racks across one AZ or multiple AZs. Right? Again, never use that one. Maybe some of you have. If you have, please let me know the use cases where you had them. And the question is like, does this really matter at the end? Because that's the most important question. Like, what are we going to get? So these are Amazon statistics because I couldn't share the original ones for obvious reasons. But this is TCP round trip latency. We're going to see packets per second and UDP latency. So the red lines are pre-CPGs and the green lines are after CPG. So you're going to see roughly a third reduction in latency just if you're going to introduce CPGs. That's a no-brainer if you're doing high-performance workloads, like zero effort for you. Right? Except the but that if the rack goes down, you're in trouble. I wanted to say another word, but I can't. The same goes for UDP, right? A little bit, almost more than around 40%. But the packets per second, because your latency decreases by a lot, right? You almost get like 50% improvements in packet processing rates than not using placement groups, right? So this is where it became a no-brainer for us to go down this route. And if you are going down this route, experiment. Like, we'll talk about this, and it's a very good point on all the slides that we're going to go through today. So placement groups are a fairly quick and easy win. If you want to increase application performance, there are some consequences here. And your mileage may vary depending on the workload and the underlying interfaces that you use. So the consequences, availability is one. So if you're going to use cluster placement groups, if the rack goes down, you're in trouble, right? So then the question is, how are you going to handle your redundancy? Are you going to have a parallel deployment? Are you going to have a pilot-like deployment? Are you going to have no redundancy at all? So what happens when the rack goes down? What's your backup procedure plans? Right? This obviously influences costs, right? Because you need, if you want to have a full backup, full redundancy plan, you have a full deployment somewhere else. Double the amount of instances, double the money, double the everything. Right? So keep this in mind. Always consider what your risk appetite is if something goes down here. And we also did like one option because this was around the time when the 5th generation, so the Nitro hypervisor actually came out. We were fairly concerned about how do noisy neighbors influence your workloads, right? Bear in mind, this was C5 instances just came out. They were fairly new, like ENA adapters came out. Nitro was new, like we didn't know anything about Nitro at the time, right? So we did experiment with dedicated hosts. Has anybody used dedicated hosts? Perfect. So what are they? You basically buy an entire physical server from AWS. So it's not like an EC2 instance where you click and deploy C5 extra large. No, you get an actual one-use server that's dedicated for you to use, fully allocated to your account, right? And you can have AWS's hypervisor on it, you can have your own hypervisor on it, you can do whatever you want with it. You have your own networking interfaces, everything is yours, right? So you can influence the entire stack. When do you usually use them? Some are for compliance reasons, where you must have a single tenant infrastructure. Like one is for if you have very old licenses that are tied to physical cores, not virtual cores, that may be a use case. And workloads requiring consistent performance, which was the use case we went with because we didn't know which neighbors we're going to have. That was basically our use case at the time. One thing to note with with physical servers, right? You can put a whole bunch of VMs on them, and depending on the type of server you buy, but it's not like your ordinary VM that disappears when you turn it off. Right? A dedicated host is yours for the amount of time that you buy it for, which is usually 1 or 3 years. So if you get it wrong, it's very expensive, right? So this is not something, yeah, we're gonna try and see what happens. No. Make sure you actually need it. We were in a very fortunate position because we experimented with everything under the sun, and our instances were 9 extra large and 18 extra large, no sorry, 12 extra large, and physical hosts, because our CTO just basically said, make it work and money is not actually a problem, right? So we had the opportunity to experiment with this, right? But if money might become a problem, this gets really expensive, like really fast, right? If you mess up your capacity planning, you can't like really return the instance. It's tied to your account. So you don't have all the instance types. So if you have some obscure stuff that you want to do, probably not going to work. And you own all the maintenance parts. So that's an additional operational overhead here, right? And this is actually what we found along the way, that you cannot influence placement of dedicated hosts. So you buy the box, and you can be like the best. You can spend millions like we did with AWS. You can go to your TAM, you can go to everybody and say, hey, we just bought like a bunch of physical servers. Can you like make sure they're in the same rack? No, it doesn't happen. AWS had a lot of bad experience with this in the past, and they just decided they're not gonna bend this rule for anybody. So even if you buy, if you have a way of doing this, please let me know. Like we tried everything under the sun, and in the end, like we just got really lucky with placement, which we could never replicate again in production. Anyway, so your mileage here may really vary if you're gonna do high performance with physical boxes. Oh, and by the way, this is always a two-way discussion, so if you have any questions, please interrupt me, because otherwise I'm just going to go on, and it's going to get boring. Any questions so far? No? Pretty standard stuff, right? Then one of the things that came out with Nitro was enhanced elastic network adapters. So elastic network adapters were when AWS went from Xen hypervisors, which you actually had noisy neighbor problems, to Nitro and KVM hypervisors, where the noisy neighbor problem kind of went away. I can't really share the details there. You also got the availability to run ENA on HVM. Yeah, there you go, AMI images, right? And if you turn it on, basically what it does, it allows your virtual network interfaces to talk directly to the host OS, bypassing the hypervisor, right? So some resource sharing obviously has to work, because you still have a lot of VMs running on the same physical machine, right? But you're going to have better latency because you bypass this stack here, right? So it uses like single root input-output virtualization to achieve this. We get much better networking performance, better latency, better packets per second for free, right? But it is not enabled by default. The AMI has to support it. Maybe you have to build the drivers for it, for your particular workload, and restart the thing, and yada yada. It's a process, right? So these are the commands that if you want to run to see if your instance actually supports it, if your image actually supports it. It's all very much documented. If it does, turn it on. If you want to know if it's already running, this is the command, right? If you see ENA, driver ENA, then that's it. You won, right? And then this came out. Like, was it last year? Or 2 years ago, maybe somebody knows, but it's fairly new. And on paper, like, it does great things. So these are AWS bullet points, so it can push 25 gigs over a single TCP connection. Wow, you're gonna have 85% better latency improvements against not using it, right? And how they actually did this. So I'm a networking geek, so I like TCP and UDP and how everything works, and I actually taught this for 15 years. So they developed their own protocol, which is called SRD, like Scalable Reliable Datagram. And if you know like UDP, it's called datagram because it doesn't, as a part of the TCP segment, the datagram does not have that many headers. Like, it's very lightweight, right? It has no You send stuff, you don't get any confirmation back, so it's unreliable. But it's very lightweight. That's why you have much better throughput. That's why voice used it in the past, video used it in the past before more efficient protocols were developed, right? But UDP is unreliable, whereas TCP is slower but reliable, right? So SRD is kind of like a bastard child of the two, right? So it has datagram transport, so very light headers, right? But it is reliable, right? But whereas TCP reorders the segment so that they arrive in the correct order, like SRD does not do that, right? And then relies on the client to jumble them up in the correct order once they arrive. What I also did was, so if you can imagine, like you have a whole bunch of routers, right, that traverse your network. So when you do like one TCP connection, usually it's always going to go through the same pathways, right, and then back again. SRD, what it does, if you send 100 packets, it's gonna every SRD datagram is gonna go maybe through a different pathway. So you're gonna see like almost parallel datagrams flowing from source to destination, and then the destination client needs to put them together again. So if you have a big data set that you're sending, like a big chunk of data, that's very good for you, right? Because you can reorder that fairly quickly. If, like us, we are sending very small pieces of data back and forth, the reordering of datagrams is going to kick you in the ass, and this is going to be significantly slower. Your workloads are going to be significantly slower if you actually enable this. So the point I want to add, enabling this, your mileage may vary. So depending on your workload that you have, right? Try and experiment with this. And here are some curveballs that we had along the way. This one took me and the team quite a few days to figure out. The magically disappearing packets. Has anybody else had this issue? Yeah, how was it for you? Painful, right? You have no idea what's happening. So we were monitoring everything under the sun on an instance level. So all the network connections, bandwidth, packets, everything. And then exchange, like we had a lot of bursty traffic. So like today, Bitcoin like really went up. So this is the time where you have lots of trade, lots of traffic. And we started getting a whole bunch of errors and retransmits, and our clients nagging us that orders are disappearing, like something is not okay with our stack. No alarms rang on our side. Like nothing, not a zero, right? All right, so we started trying to figure out what it was. Our metrics, all okay in the green. Then we started looking at CloudWatch and the metrics there. And you have a few that are, like written in fine print, because nobody's gonna give you their limits, which is amazing. And one is bandwidth allowance, in and out, packets per second allowance, and connection track, so how many parallel connections you can have running at the same time. So bandwidth, obviously, how many, if we go back into ENA stuff where multiple VMs share the same physical connection, it makes sense. Like you cannot utilize, if you have 4 VMs running, you cannot utilize 100% of that connection. So you need to impose certain limits. The problem is that AWS does not tell you how high they are or how low they are. So once you reach this, you're going to see in CloudWatch your metrics are just going to peak, and everything else is shaved off on the Amazon network backbone. You can't do anything about it except increase instance size. Shut it down, increase instance size, bring it back up. That's the only thing that you can do. And then again, hope to God that it's going to be placed into the correct rack, which was a problem for us. It took a lot of experimentation to actually get it right. And this is the most amazing part, no official docs exist. You can talk to your TEM guys, your contacts at AWS. They might share this with you, but these also change from generation to generation to generation. So it's never a static number. So how was your experience with this? Yeah.
Will this be affected example, if you have multiple heavy load users on the same
No.
instance?
So in principle, the way the Nitro hypervisor does it, it's going to equally divide all the exactly equally all the resources against all the VMs running on it. So if you run, for example, a C4 extra large, C5 extra large instance, you're going to be placed on the exact physical server that is also running C4 extra large. You're not going to have a mix and match of sizes inside one physical server. That's why they can equally divide the bandwidth allowance stuff on the interfaces, right? But again, we couldn't get those numbers, so I'm not sure how your experience was.
Yeah, usually limits are tied to instance sizes, but you can go your way around it. Just switch between Intel and AMD, and then for sure you'll be.
Yeah, but that's the different instance, right?
Yeah.
So. But yeah, this one was very problematic for us. And the second one is, if you really go down into performance and networking stuff, it's very, very hard to reproduce constantly. So we had a whole bunch of pre-production environments where we did a lot of stress tests, and they were the same as production, even in sizes, right? And we could never reproduce on a one by one basis the performance, right? So testing is required here a lot to find the combination that works. Even within regions, you're going to have performance differences. Even within AZs, you're going to have performance differences. So you're going to notice this if AWS like expands an AZ or like has maintenance on it, you're going to see wild latency spikes if you run a lot. So experiment as much as you can, test as much as you can before going live. Right.
Excuse me.
Yeah.
Can you maybe share some numbers, like how big or low were your latencies and what did they affect you, totally throughput, the number of connections or transactions that you need to do?
Even if I could, I'm not at Bitstamp anymore, so I don't even have
No,
that
I
data
just-
anymore.
Because I work with the companies that
Mhm.
run on bare metal, like the Thorn, and I know what
Yeah.
huge numbers are. And then in AWS, I work with workloads that are quite big,
Yeah.
and I never had issues with it. But I imagine that you guys had orders of magnitude larger number of the.
So the issues that we had with the bandwidth stuff, that was C5 9 extra large and also one more than that. So that, and basically you can place two C5 9s on one physical box, and then I think it's a 12, which is
How
the
much
single one.
Would you expect to get, and how much would you be getting it? Just like the rough numbers to get the.
I
idea.
actually don't have that in my head anymore.
We're talking tens of gigabits or
Yeah.
hundreds of gigabits.
No, it's approaching 100. Yeah.
That's a lot.
Yeah, because we had our infrastructure at the time, so again, this was 2018, was a little bit not optimized because we did have this one big component that was, everything was in memory there, and all the traffic had to go through it for everything, right? And there was obviously a hot standby ready, but it couldn't run in parallel because it was doing in-memory processing. So, and if you hooked up something like, a store radius, whatever on it, it just destroyed your latency. So you can imagine all the exchange traffic, 4 million users connecting simultaneously, went through one server at a time. All the WebSocket stuff, everything, right? So that was a lot of traffic. It was a design flaw at the time, but we had to deliver that blog post, so you had to cut some corners. But yeah, the rough numbers, I can ask like if the guys are gonna share them, but I don't know them anymore. All right, so this, how to offer your best performance to customers, this one came a little bit after, like a few years after, because it wasn't available at the time. So if you can't really optimize, there are limitations that you can do inside your data center about optimizations. But the best solution that you can do with the clients is to bring them in, actually. Right? And this is a feature that was not available up until recently. But if you use So what's missing here, right? You can run cluster placement groups, right? And I think it was 2 years ago, I think. You had the ability to start sharing cluster placement groups with different accounts. So if you're using AWS organizations, as you should, one of the components of AWS organizations is the resource access manager. So the stuff that lets you share resources, not only within your organization, but with other organizations as well, right? So for us, we had this question, like market makers that were bringing in a lot of money started asking how can you bring us closer to your matching engine? Right? How can you give us an edge? Right? And turns out what you can do, you have your own compute, you have your customer's compute, you can put that compute in the same rack, right? What's missing in this picture?
Connectivity.
Exactly. Like the connectivity is missing. So what are your options?
Peering.
Why peering? You have a lot of options, so why did you say peering?
It's an option.
Yeah, but why did you say peering? Like, I'm actually interested.
You asked what the options are. That's the first option that I can do.
All right.
It's the easiest one, yeah.
Actually, it's not the easiest one for customers, but it's the cheapest one, right? You have a lot of options. So you can do transit gateway, which is by far the easier, but it's super expensive. You can do private link if you want, but it's super expensive, right? But if you're gonna do VPC peering, so here's the catch. You obviously need to do the peering connections, but VPC peering inside an AZ is free for your traffic. So you're not gonna pay anything, no egress, no egress costs, nothing on a network level. So it's free if you're gonna exchange a lot of data, right? Right, so how do you share this stuff? Through RAM, right? Resource Access Manager. It's fairly simple. You just specify the resources that you want to share. You set permissions on them. You share that with accounts, organizational units, users, whatever you want. I traditionally used RAM for sharing subnets. So like we had tens, hundreds of AWS accounts. We had one networking account that created all the underlying networks. And then we share those networks with developer accounts, with BI accounts, data engineering accounts, and so on. This is the traditional use case. We also use this for sharing images, and a whole bunch of other stuff. And also CPGs, right? So it's fairly easy to do. There's also a very good presentation I gave last year about this if you want to go through it, because I'm not really going to go into much of a deep dive right now. But yeah, since October 2022, you can start sharing placement groups with other accounts, which was a very good feature for us, right? How to do this, it's fairly simple. So first you create the CPG, then you go to RAM and you say, yeah, I'm gonna share this CPG with an AWS account. You put an AWS account there. And on the other side, you have to accept the resource share, right? And if you're gonna go through some details, you'll see that the CPG that just appeared magically in your account is a shared one. So if you're gonna deploy your EC2 instances here, they're gonna come up in my racks, for example, if I share the CPG with you. Right?
They're not, so you say your racks. They're not your racks. It's just your stuff is guaranteed to be there.
Exactly.
But
Yeah.
they're not dedicated to you, the rack.
No.
Okay.
Yeah, so CPG, when you say I'm gonna put a CPG, means that your compute is gonna be placed under one spine. It could be one or more racks.
Understood.
Yeah.
Just
Yeah.
differentiating between, it's not yours.
No.
Your
It's
stuff is
shared,
gonna be
but
neat-
exactly.
on the same stuff as yours.
Exactly.
The rack itself is not yours.
Exactly. All right, so one thing to note when you're gonna do this, right? And if you're gonna be checking stuff, if I'm gonna share one AZ with you, it's probably not gonna be the same AZ name for you on the other side, right? So be mindful of this. This is when you're gonna do verifications, this happens a lot. So AZs are randomly named every time you open an account, right? So AZ ID is not going to be tied to the same AZ name across different accounts, right? So just be mindful of that. All right, so this is what we actually ended up doing. So sharing compute with market makers. And we started using VPC peering and sharing that as well with customers. This is how we brought them closer to us as well. And then what else can we do? Right, so this was more or less like networking stuff and RAM stuff, and obviously you can do optimizations here. But the most brutal stuff you can actually do is on kernel and Linux level. Right? There are a lot of guides here, a lot of performance optimizations, and everything depends on your workloads. Right? There is no silver bullet for this. The basic points that you can do: use HVM AMIs, because these support ENA adapters. So turn on enhanced networking if not already supported. Use as fast drives as possible. Just be mindful of NVMe drives because they're ephemeral. So shut it down, you're going to lose data. You can tweak memory. You can turn on huge pager, so how much stuff you can put in memory. You can tweak networking, so the maximum transmission units as long as you are on the same subnet, so not passing through layer 3 stuff. When are you going to do CPU interrupts? How many stuff are you going to accept in your ring buffers on the interface level? Right? You can tweak your CPU. How deep are your threads going to go to sleep, if they're going to sleep at all? Right? All of this stuff you can tweak, and monitoring here is your friend. If you have not heard of Brendan Gregg, he's the author of this flame graph. It's a very good repo. It allows you to shows you how to instrument your processes and how to display very good performance graphs to see where your bottlenecks actually are happening. So this is actually a practical example of what you can do. So this is our baseline. I think this was from Mark Richards, which is a performance engineer at AWS now. This is our baseline. So we can do like roughly 200,000 requests per second, and we can transfer 33 megs. Right? After you do the optimizations, this is the most brutal stuff you can do. Right? It pretty much it's five times faster. So you can do 1,200,000 requests and roughly 160 megs per second.
Sorry, is that Apache bench?
No, this was a custom test. Yeah. But there's a link at the very end if you want to go through it. So you can do this, you can do a lot of stuff on a kernel level as well that's going to bring performance drastically up. But again, with all of these, with everything I said today, your mileage may vary depending on your workloads. Right? Very rarely there is a silver bullet for everything. There are a lot of credits here. Like when we actually put the matching engine in the cloud, we were the first to put an on-prem matching engine in AWS. There's a whole bunch of stories around this. We couldn't have done it without AWS's support. Cinnober, Nasdaq, and a whole bunch of talented guys at Bitstamp that helped us do this. So if you want to take some pictures, these are, I guess, the most important codes. I'm just going to pause for a bit. I'm not sure, Paula, do we share this? Probably, right? Yeah. All right, so everybody's going to get it. Perfect. And the last one is thank you. Hope it was interesting. And let's stay in touch. This is my LinkedIn if you want to connect and continue this session or anything else that you might have. And that's it for me.